So thanks a lot, Angie, for this very nice introduction, and also to you and to Patrick for inviting me to give a talk in this very nice seminar series on ISS and related concepts. So today I want to share some insights into an input-output to state stability notion, in particular an incremental version of that, and some time-discounted variants. And in particular, also show you how it is useful for the analysis and design of optimization-based state estimators, in particular moving horizon estimators. So this is the outline after a brief motivation, right? In the first part of the course, I will briefly introduce that concept of incremental input-output state stability, and also some recently employed time-discounted variants thereof. And then study one of these in a little bit more detail, right? Show you an equivalent Lyapunov function characterization, and in particular, some numerical verification to compute such an incremental IOSS Lyapunov function using tools from Riemannian geometry. And then in the second part of the talk, so hopefully I have to say this is not too technical, right? And I don't lose you in that part, but since it's an ISS seminar, I think you're all experts in that area. So I think that should be fine, hopefully. And then in the second part of the talk, I will show you how we actually employ that in the context of moving horizon estimation. So let me start with a brief motivation, right? If you want to design observers for nonlinear systems, right? So we have a system with state X, right? Some disturbance or noise inputs U, right? Which affects both the system dynamics and or the measurements, right? So I subsume them into a joint variable U. And also some known time-varying signal, like control signals, for example, denoted by D. Right, then if I take measurements of some output functions y that I can measure, right, the task of the observer is to reconstruct the internal system states, as you all know, from the measurements and the control signals that I have available, right? And this is denoted by x hat. Now, as you all know, desirable properties of the state estimation error, which I define by E x hat minus x, are that it should converge to 0 if I don't have any disturbances. Right, so having here this, the norm of the error should decay to 0, right, is a classical KL bound. And then if the noise is small, of course, also the estimation error should become small, right? So that's the classical ISS-like robust stability bound for the estimation error that I would like to have, right? That the estimation error is bounded by the maximum of this decaying term of the initial error and the supremum norm of the disturbances. Now, why do I say an ISS-like bound and not why don't I say the estimation error is actually ISS? Well, because in the end, I want to study general nonlinear observers, right? In particular, optimization-based observers, where the estimate x hat comes from the solution of an optimization problem. So in particular, the error does not follow any given error dynamics, so not a dynamical state space representation, right? So I cannot say the error system is ISS, but basically the error satisfies this ISS-like bound, right? And as was already shown in this introductory paper by Eduardo Sontag and Wang in 1997, right? A necessary condition for the existence of such a robust state estimator is this notion of incremental input-output to state stability. Now, back then, this was shown actually for a setting where the observer is also a dynamical system, right? So a full order state observer, right, of the same order as the system state. And recently in a nice work by the group of Jim Rawlings and Andy Thiel, it was shown that actually this necessary condition also holds for these more general observer mappings, right, including optimization-based estimators. And in particular, in the context of the latter, right, so moving horizon estimation, this notion in previous years, in the last 10 years, has been established or has established itself as the widely used detectability condition, which was used both for the analysis and the design of these type of estimators, right? And that's the subject of today's talk, right? In the first part, as I mentioned, I will again discuss this notion in a little bit more detail and then show how we really use it for the design of these optimization-based state estimators. So let's start with the setting, right? So it's the standard setting. I have finite dimensional systems. Mostly in the first part, I work with continuous time systems. In the second part, also with discrete time systems, nonlinear systems, right? Given by this ordinary differential equation here with initial condition chi. And again, so the states denoted by x, the outputs by y, and time t. And as I said, u is an input signal, right? Disturbance inputs, measurement noise, so disturbance input signal. And d is some time-varying parameter signal that I know, for example, control inputs. So the standing assumptions are the standard ones, right? So u and d are locally essentially bounded functions defined on this open interval from 0 to infinity, and taking values in some closed sets u and y, which are subsets of our m and our q respectively. And for simplicity, we assume that the system is forward complete, right, for any input signals u and d, right? This is just a technical condition, and we can also extend everything to the maximal interval of existence, but just this would complicate notation, so I don't do it here. And as usual, I denote the solution, right, x of t to my system here sometimes I use this long notation, x of t chi u d, right? So the solution at time t starting at the initial condition chi and being driven by the disturbance input signal u and the control input signal d. And the corresponding outputs I define analogously, right? So y of t chi u and d, and the complete output signal, this notation I also sometimes use throughout the talk. So the complete output signal I then denote by y or subscript chi u d. Whoops, sorry. And again, standard notation, right? To abbreviate the norms, I just use this standard absolute value terms here instead of the two norm. Actually, everything, of course, also holds for other norms. But later on for the verification, it's more direct to write it for a two norm. But of course, everything also holds for other general p norms of the vectors. And this I use for the essential supremum norms or standard notation that I guess you are most likely all familiar with. Now, this is the notion of input-output state stability, which was introduced by Sontag and Wang in a very nice systems and control letters paper in 1997. So, and it's as follows, right? So we say the system is incrementally input-output state stable, or in short, IOSS, if there exists a KL function beta and two K infinity functions gamma 1 and gamma 2, such that this inequality holds true, right? And what does it mean? So that the difference between two trajectories starting at two different initial conditions, chi1 and chi2, and being driven by two different noise sequences u1 and u2, right? At each time t is upper bounded by the maximum of these three terms. The first one is the standard decaying term, right? A KL function in terms of the difference of the initial condition. And then these two gains, gamma 1 and gamma 2, of the supremum norms of the difference of the input signals and the output signals, right? And this should hold for any pairs of initial conditions, chi1, chi2, and any pair of input signals, u1 and u2. So, and this is basically a detectability notion. Why is that the case? Well, let's first look at the case where both I apply the same inputs, right? And then if the outputs are the same, this means that also the states asymptotically need to converge to each other, right? So that's the classical distinguishability property of observability or detectability in that case, right? If I apply same inputs and the outputs are also the same, right? Then also the states must converge to each other. So in some sense, if you want, the output difference is some type of metric for the difference of the states that I obtain asymptotically, right? And as such, inherently carries information about the detectability of nonlinear systems. And as I already mentioned previously, right, on my motivation slide, it was already shown in this paper by Sontag and Wang in 1997 that this condition is in fact necessary for the existence of a robustly stable state estimator. As I mentioned, this was extended recently in this work of the group of Jim Rawlings, also for more general optimization-based estimators, so general estimator mappings. Now, in recent years, actually, so this is the standard notion, right, which has been around now for 25 years or so. And in recent years, some time-discounted notions of that have been proven to be particularly useful, especially in the context of optimization-based state estimation. And these I want to show you on the following slide, right? So the main difference compared to this definition here is now that I just allow for time discounting, right, in these two disturbance and output gains, right? So in gamma 1, instead of having k infinity functions of the supremum norm, I just use the supremum of a KL function, right? So basically, which discounts past input and output differences. And that's here basically what I have on the next slide, right? So I just use a shorthand notation, delta x, and also delta chi, delta u for just the differences, right? Just to shorten the notation. And so basically, this is a time-discounted version of that incremental IOSS we saw on the previous slide. And as I mentioned, the difference is here in these two terms on the right-hand side that I allow for a time discounting, if you want, right, of these gains of the output and input differences. So basically, I discount output and input differences which are further in the past. Now, why is this of interest, right? So actually, in recent years, in the moving horizon literature, this has been first introduced and analyzed for discrete time systems, right? So we first discussed that in an MHE paper a couple of years back, in a CDC paper, and then we formalized it. And also there was this nice work by the group of Jim Rawlings, Doug Allen, a PhD student, and then also co-author Andy Thiel, where they further analyzed that. And in fact, it was shown in this paper that in fact in discrete time, this time discounted notion is in fact equivalent to the classical incremental input-output state stability notion that was originally proposed by Sontag in 1997. Now, why is this time discounted notion of interest? Well, as I will show you in the second part of the talk, especially using this time discounting is particularly useful because it allows for much less conservative stability guarantees in the context of the design of optimization-based state estimators. Now, in continuous time, actually, we recently introduced and showed that this is also useful, again, in the context of moving horizon estimation if we use an integral version of incremental IOSS, right? So compared to the previous slide, right, where I had this time discounted notion, what we have now here is an integral version, right? So here you see on the right-hand side, the main difference is that we use integration here, right? So if you want, in particular, if alpha u and alpha y, which are k infinity functions, are quadratic, then this would be an L2 to L infinity type property, right? So we just use the integral variant of that. Other than that, you see that the time discounting here is now exponential, but this is without loss of generality, right? Because on the left-hand side here, we also have a general k function. And as you all know from standard Lyapunov theorems and also from Sontag's KL lemma, right? So that basically in certain coordinates, an exponential decay is without loss of generality, right? So here really the difference here is that we have this integral variant of that. And as I will show in the following, this is a useful property, especially in the continuous time setting, also for the design of suitable nonlinear estimators. Now, in fact, in the discrete time case, all these three notions are in fact equivalent, right? So this right equivalence here, I already mentioned in the previous slide, this was shown in this work by the group of Jim Rawlings. And the first equivalent is actually fairly easy to see in discrete time, right? Because loosely speaking, right, because discounted maximization and discounted summation are in fact equivalent in discrete time, right? So in discrete time, instead of an integral, we have a sum here, right? And now if I have a discrete time signal z, which maps from the natural numbers, right, to the non-negative real numbers, whoops, sorry, then if I look at the discounted maximization of that signal in the interval 0t, right, of course, this is trivially can be upper bounded by just summing up all these terms, right? So taking the sum from tau equals 0 to t. And then what I can do here is just split up this factor lambda to the t minus tau into two factors, square root of t minus tau to the power of t minus tau times square root to the power of t minus tau. And then pull out one of these factors times that, just take the maximum, pull it out of the sum, and then for the rest use the geometric series to arrive that this is just less or equal than 1 over 1 minus square root of lambda times, again, the maximum, right? So this basically shows what I said, that in discrete time, discounted maximization and summation are basically qualitatively equivalent, right? And this is why this integral variant, or in discrete time, it's a sum, is just equivalent to the non-integral variant. Now, in continuous time, this is in general not true, right? And so it's so not difficult to show that this implication still holds, right? Because the second inequality here, this one, also actually holds in continuous time, right? If I have here an integral, then a sum, I can still do the same thing. But this first inequality is in general not true in continuous time, right? We all know that there are L2 signals which are not L infinity signals, right? So that's why this inequality typically does not hold in continuous time. And that's why so the notion of time discounted integral incremental input output state stability is really in general a stronger property than the non-integral version of it. Now, what's the meaning of all that, or why is that actually interesting? So as I mentioned before, right, specifically in continuous time, using this integral version is quite intuitive and interesting. Why? So first of all, it's directly related to classical notions of observability, detectability, right? So for linear systems, not surprising, it's equivalent to just a standard detectability. But also for nonlinear systems, right, you can also relate it to maybe more classical notions of observability. For example, if you look at the observability map, right, and assume that this is invertible, which is a standard notion of observability, right, you can show that this actually implies that the system is in fact has this integral incremental IOSS property, right? So the standard observability condition is a sufficient condition for the system being incremental integral IOSS. And in particular, right, I will show you next, it also has this integral variant and equivalent Lyapunov function characterization. And in particular, we can also systematically verify it using LMI conditions, using tools from contraction theory or Riemannian geometry, which I'll also briefly show you in the following. And as I now mentioned multiple times, that's the second part of my talk, is particularly useful in the design of moving horizon estimators with strong stability guarantees. So this was the first part of my talk. Right now, I want to go a little bit in more detail into this time-discounted integral version of IOSS and show you an equivalent Lyapunov characterization, and then in particular the numerical verification using LMIs, and then move on to really discussing optimization-based state estimators, in particular moving horizon estimators. So this is basically the definition of a incremental integral IOSS Lyapunov function, right? So I guess it's not surprising to you since you're all experts in ISS and related concepts. So we say that such a function U, right, which has two arguments, is such a Lyapunov function if it is continuous, and if there exists 4 k-infinity functions and the constant lambda, such that these three inequalities hold, right? The first ones are the classical lower and upper bounds, right? In terms of the difference, right? So the delta chi is again chi2 minus chi1, right, as before. And this is basically the standard dissipation inequality, right? Basically where I have these gains here, the nonlinear gains of the output and input difference, right? So for the incremental version. And 2 remarks I have for that, right? So first, that we have an integral form here and not the differential version, as maybe is more common, and only require continuity instead of smooth ISS Lyapunov function. This is motivated by works from David Angeli 15-20 years ago, who studied in incremental versions of ISS, so both ISS and integral ISS, right? And typically this allows to treat also non-compact input sets where typically smooth converse theorems fail or might fail. And the second remark I want to make is again that having this exponential decrease here, right, is again without loss of generality, as you know from standard Lyapunov and also ISS theorems, right? So basically this condition is equivalent just to the existence of a continuous function U tilde, which satisfies maybe this more common looking dissipation inequality here for some k function or k-infinity function alpha 3 instead of having here this exponential decrease. So again, in certain coordinates, right, an exponential decrease of the Lyapunov function is without loss of generality.
Sorry, quick question. Could you make it local in Lipschitz as well, the U?
We did not manage.
Okay, thanks.
Yeah. So we only could prove that it's continuous. We could not make it local in Lipschitz. But yeah, maybe we just could not do it. Yeah, so but we couldn't do it. So yeah, and that's basically the theorem that we proved in a CDC paper, which we showed in Singapore last year, an LCSS paper, right? Not too surprising, right? That's, you know, from many other variants of ISS and related concepts. But the necessity part was a little bit different, or partially, especially showing continuity, right? But actually the statement is as expected or as wanted, right? That the system has this integral form of incremental IOSS if and only if there exists a corresponding Lyapunov function. Now, as always, right, the sufficiency proof is trivial. And the necessity proof uses and combines similar arguments from previous converse results, in particular from incremental integral ISS and from integral IOSS, where there's an archive paper by Ingalls. And basically, I'm not going into detail here, right? If you're familiar with converse theorems, then this might look familiar to you, right? So we define a Lyapunov function candidate by taking the supremum over all disturbance sequences and also known control signals, right, of this right-hand side expression here, right? And then we can show that this satisfies dissipation inequality. Now, what is different to the existing literature, right, and also to these two works here is how we have to ensure continuity, right? Why is that the case? Because typically, or here, local Lipschitz properties of the vector field F are exploited, which we cannot do here in our case, right? If we use the incremental version together with outputs, and that's why we need some other continuity type conditions on the on our vector field F. So basically a K continuity property, if you're familiar with that, and this K function has to satisfy certain integrability properties. So it's actually related to the Oscar condition, if you might know that, which is also used in literature to establish existence and uniqueness of solutions of differential equations. So I'm not going into detail here, but this was the main technical part, and which was also different from existing converse results in the literature. So now this is basically nice because as expected, or as for other well-known ISS and related concepts, right, we have an equivalent Lyapunov characterization, and this we will later use now in the design of these nonlinear state estimators. However, to this end, I need to compute a corresponding ISS Lyapunov function. And as you all know, right, this is difficult for general nonlinear systems. And what we propose is to use tools from contraction theory or Riemannian geometry, right, that have been proposed also in recent years, how to compute Lyapunov functions, right, for contracting systems. In particular, right, if a system, right, without inputs and outputs has a property that it is exponentially incrementally stable, so meaning all the trajectories, right, converge to each other, then the system contracts basically, right? And then we can compute a contraction metric and use this then for analysis of the system and so on. And I will show you in brief in the following how we can also extend that to the case with inputs outputs, right? So that we can find input output to state stability Lyapunov function, right? And in the end, this will result in LMI conditions in the case that we have a smooth ISS Lyapunov function, and in case that we have actually an exponential ISS property, right? So for this special case, this can be then reformulated as LMI conditions, as I will show you now. So how does that look like, right? So I consider again these two trajectories, right? Starting at two different initial conditions and being driven by two different noise signals. And as a starting point, right, we consider some path that for some fixed time ti connects x1 of ti and x2 of ti, right? So here it's depicted for a time t1, right? So for s equals 0, this path starts at x1 of ti, and for s equals 1, it ends at x2 of ti here. Now, for a fixed path variable s, right? So this point on the path evolves in time according to the original nonlinear continuous time dynamics. Right now, here depicted in this cartoon for a time t2, right? And due to the nonlinearity of the system, right? Even if I start with a straight line here, this results in then some curved path in general, right? Now, what I want to look at is at the path derivatives, right? So at the derivative of this path with respect to the path variable s, right? So I need a continuously differentiable path, of course, to that end. Right, but basically what I want to look at is at delta x, which is just a partial derivative of this path with respect to s, and also then delta u and delta y, which are not shown here, but these are basically paths connecting the two input and the two output signals, right? And then delta u and delta y are again the derivatives of these input and output paths with respect to the corresponding path variable. Now, just using the chain rule, right, it's easy to see. So I hope you don't get disturbed by the zoom window that is in the corner. So hope now you can see, I think, the whole slide, right? So just using the chain rule, it's easy to see that these differential dynamics are just linear dynamics, time varying, of course, right? But this is basically, and this is what's called the differential dynamics, and these ABCD matrices are just the Jacobians of our nonlinear vector field F and the output map H evaluated at T and S, okay? Now, the idea is to first find an IOSS Lyapunov function for these differential dynamics. And then once this has been done, translating it to an incremental IOSS Lyapunov function for the original dynamics, right? So let's look how to do that, right? In order to find a differentiable Lyapunov function, right? In that case where we have exponential IOSS, right? That's why we use basically this quadratic function, right? So it's quadratic in these path derivatives delta x. And this matrix P of x, this also can actually depend, is allowed to depend on the state x. But what we need is that we have these quadratic lower and upper bounds, right? So basically that this matrix P is uniformly lower and upper bounded, if you want, by two matrices P1 and P2. And then that we basically satisfy this dissipation inequality, which when satisfied gives us the standard IOSS notion for the differential dynamics, right? And if you want, right, in the case without inputs and outputs, this W would be the contraction metric. Right, so I'm not sure whether I would call it like this, right, in the case that we have also inputs, outputs, but you could call it like that if you want. Now, since the differential dynamics are linear, this can be translated into a set of course, infinitely many linear matrix inequalities, right? Why infinitely many? Because they have to be satisfied or be verified for all x in our domain. Now, of course, this is not tractable, right? But now either using gridding techniques, if you're interested just in some compact subsets of your state space, or using suitable SOS relaxations, sum of squares relaxations, right? This can be then, again, if you have polynomial dynamics, or if you use a polynomial approximation of your dynamics, right? Then you can actually transform that into something that is computationally tractable and you can solve for numerically. Now, given that you have this IOS Lyapunov function for the differential dynamics, what we need to do is go back and relate that to an incremental IOS Lyapunov function for the original system, right? And basically the idea is to just integrate this differential IOS Lyapunov function along the path and looking at the minimum, basically the path with minimum energy, if you want, right? So basically we consider the energy functional u, right, which is just the minimum along all possible paths, right, connecting basically x1 of t and x2 of t, and just over the integral of this function w that we found for the differential dynamics. Right now, and this one can actually show that this then is in fact a valid incremental IOS Lyapunov function for the original system. Now, this is nice, but the problem is I can in general not evaluate that or find an analytic closed form expression for that, because that's highly nonlinear and I can typically not solve this analytically. But under certain conditions, we can show that actually we can find suitable upper and lower bounds for this Lyapunov function, right? Which are exactly those matrices from the differential IOS Lyapunov function. Right, so that under suitable conditions, this function u is actually also lower and upper bounded by these weighted quadratic difference of x1 and x2, and weighted with these exactly the same p1 and p2, and also the differential of not the differential version of the dissipation inequality is satisfied with the same constants kappa, and the matrices q and r also stemming from the differential IOS Lyapunov function. So this means that we cannot explicitly compute the incremental IOS Lyapunov function itself, but the required lower and upper bounds, and also these constant and the two matrices appearing in the dissipation inequality for the Lyapunov characterization of incremental input-output state stability. Right, and then of course just integrating that and using comparison principle, this directly gives this integral version that I had in the definition of the time discounted integral incremental input-output state stability. And of course, then just this directly also gives me the suitable bounds in the IOSS What was there a question?
So can I ask you a quick question?
Yes.
So a couple of things. First of all, the p of x in the differential IOS Lyapunov function, how complex would that be when you do the sum of squares and so forth? Because you will have a derivative of that, right? With respect to time. I mean, you need the gradient. You will talk about it?
Yeah, that's a good question. I mean, typically, yeah. So it actually, also that's what I mentioned here, under certain conditions, right? We actually require, so these conditions are actually two, that the output equation is linear, right? Or actually can be made linear under suitable transformation. So this might or might not be satisfied in applications, right? In many applications where you just measure a subset of the states, then this is trivially satisfied, right? Otherwise, you need to find basically a transformation. And then basically the matrix P of X needs to be suitably block diagonal, right? So in particular, block diagonal with respect to that partition of states that are measured and states which are not measurable, right? So that's basically what we need. In actually,
but I think I was talking more about the algebraic form of P. Sorry? How does a metric depend on X? It could be, I mean, what will be the algebraic form of the dependence of the metric P of X on X?
I mean, it just needs to be differentiable, but it could be in particular anything, but it needs to have this block diagonal structure. But actually, in our examples, we most often just use actually a constant function, a constant matrix P.
A constant matrix. Okay, no, that's fine. The constant matrix is fine. And also one last question. So this is all for characterizing exponential versions of ISS.
Yes.
Okay. Yes. There's no way to do this in any obvious. Well, obviously you can't use contraction theory otherwise.
Exactly. No, not for non-exponential. Yeah. Exactly. So this is just for the exponential version of it. Yes, correct. Yeah. That's what I.
Okay, thanks.
All right, so thanks for the question. So this is basically how we can verify if the system is exponentially, incrementally input-output state stable. And I will show you not the detailed computations, but I will show you some examples later for the design of moving horizon estimators where we actually computed, in that case, actually using a constant p in these examples we used later. All right, so this ends the first part of the talk, right, on this notion of incremental IOSS, right, and also some time discounted versions. Now, let me show you how we actually apply this in the design of optimization-based state estimators, in particular moving horizon estimators. So I think I don't really need to motivate nonlinear state estimation to you, right? As you know, in many applications, right, for control, if you do state feedback control, certainty equivalent, in monitoring and fault diagnosis, right, we need basically state estimation techniques. And one estimation technique which works nicely for general nonlinear systems is moving horizon estimation. Of course, there are also many others which I don't discuss here in this talk. But what are the advantages of this technique? Well, they are applicable to general nonlinear systems, right? We don't require any specific normal form or as some other nonlinear state estimation techniques. In recent years, what I will show you next, quite strong robustability guarantees, I think, have been established. And two additional advantages, if they are applicable, is that if there are system inherent constraints that we know, like non-negativity of concentrations in a chemical reactor, I can just directly incorporate that in the optimization problem to improve the estimation performance. I'm not going to consider that in the remaining slides for simplicity, right? But this can easily be done. And also you can directly basically deal with missing measurements, right? Just don't take them into account in the formulation of the optimization problem. So what's the main idea, right? I explained this in this cartoon for discrete time systems, right? So if t is the current sampling time, at each sampling time, I look back a horizon of length capital N, right? I take these past N measurements into account to solve an optimization problem, right? And computing an optimal estimated state sequence over that time horizon from t minus N to t, which I denote here by x hat of kt, right? So t after the bar is the current time at which I do the computation, and k basically is the time for which I do my estimation, right? So k goes from t minus N up to t. Right, and then once I found the optimal solution, I will show you how that actually looks like, the optimization problem that we saw. I denote the optimal solution by x hat star, and then I define my current estimate to be the endpoint of this optimal estimated state sequence, right? So this I denote by x hat of t, right? The endpoint of that sequence, and that's then my current estimate, right? And then I just shift the horizon at the next time instant, do the same thing again, and compute my next estimate. Now, of course, ideally, I would like to take into account all the past measurements, right? So from time 0 up to the current time t. But this is, of course, computationally not tractable, right? Because this would mean that at each time t, my optimization problem gets more and more complex to solve. That's why we typically look into the past, the finite horizon, right? And neglect the past measurements. Of course, we need to take into account that we neglect these past measurements by a suitable regularization of a prior weighting, which I will show you in the next slide. So, but that's the main idea. I mean, many of you, I guess, are familiar with model predictive control. Basically, that's just a dual problem. I don't predict in the future and solve my optimal control using an optimization problem, but I just look in the back, in the past, also a finite horizon, and compute my optimal estimated state sequence over that horizon. Now, so for simplicity, right, in the remainder of the talk, I consider just discrete time systems, right? Instead of continuous time systems, you can also do it for continuous time, but they're just a notation, and the formalizing everything is more difficult, right? Because anyways, you only can solve an optimization problem at discrete sampling instances. So that's why for simplicity, I directly consider discrete time systems. And so this is basically just what I explained to you in this cartoon, right? What we do at each sampling time is solve an optimization problem. We minimize the cost function for the initial condition of our optimized state sequence, estimated state sequence, and the estimated noise sequence denoted by u hat. Right, I will momentarily, in a minute, show you the cost function, how it looks like, and how it relates actually to the IOSS condition. But of course, the estimated state sequence has to satisfy our model of our dynamics. And then I compute also the estimated output corresponding to that estimated state sequence, given again just by the output maps along the estimated states and disturbances. And as I mentioned before, the current estimate at time t, x hat of t, I just denote by the endpoint of the optimal solution, so by x hat star of tt. Now, how do I choose this cost function j? before I want to specify that, let us just discuss the assumptions. And basically, I just assume that I have such a quadratically bounded, meaning ISS Lyapunov function, meaning that our system is actually exponentially incremental input-output state stable. Right, so that's just a discrete time version of that, right? Again, these lower and upper bounds, and here the corresponding dissipation inequality in discrete time. Right, so as I mentioned, this implies exponential incremental input-output state stability, and as in the continuous time case, this is verifiable using the differential dynamics of the discrete time system and then transforming it into a set of LMIs. All right, now, this is the cost function which we use in the optimization problem. So let's first look at this part, right? So this is the classical least squares type objective, but a discounted version of it, right? So, and the discount factor is exactly the one which comes from the ISS Lyapunov condition. And also these matrices Q and R are those here from the ISS condition. Now, what are these terms, right? So the second term here, this is just a fitting error, right? So penalizing the difference between my estimated output y hat and the real measured system output y, right? And this term here penalizes the estimated noise, basically, right? So if you want, that's the standard trade-off. If you want how much I believe my model and how much I believe my measurements. Okay, so it's a standard least squares type objective that has been used since many years in moving horizon estimation, now just in a discounted version, right? So I discount previous noise and output fitting errors that are further in the past. And now this first term here, this is the so-called prior weighting. And this takes into account the fact that basically I only look back a finite horizon, but I neglect all the past measurements from time 0 to t minus n. And this is basically done via this prior weighting. Again, this P2 comes again from the ISS condition here, this P2 from here. And basically, this penalizes the difference between my initial condition for the optimal current estimated state sequence to what I estimated n steps before. Right, so x hat of t minus n is the state estimate which I obtained n steps in the past, so at time t minus n. Right, and in this fact, basically, I loosely speaking take into account basically the neglected measurements from time 0 to t minus n. Now, using this cost function, actually, we can derive the following stability properties for the resulting estimator, right? So we assume, as I mentioned on the previous slide, that there exists this incremental ISS Lyapunov function, and then I have a condition how large I need to choose my horizon. Length n, right? So this was the horizon, how many measurements I take into account, how long I look in the past. And basically, this is such that this constant here has to be strictly less than 1, right? Lambda max of P2, P1 is just the maximum generalized eigenvalue of these two matrices. And such that basically 4 times this factor times lambda to the power of n is less than 1. So I can directly solve this for n and have a lower bound, which I need to choose such that in the end, I can actually guarantee that the ISS Lyapunov function is in fact also a Lyapunov function for the resulting estimation error, right? So meaning that if I evaluate this incremental ISS Lyapunov function along the real unknown and estimated trajectory, x and x hat respectively, right? It's basically decaying exponentially, right, over n steps, right? And then plus, of course, these terms, which again depend on the process and measurement noise that affects the system. And from this, actually, it's very straightforward, of course, just using the upper and lower bounds of the Lyapunov function to get this desired bound for the estimation error, right? And in particular, it's an exponential ISS-like stability bound, right, that I mentioned at the very motivation slide, that the estimation error exponentially, so the influence of the initial estimation error exponentially decays to 0, and it converges to a region determined actually by the occurring process and measurement noise. Now, let me briefly show you how we apply that to 2 examples. The first one is a rather simple example. It's just a 2-state example, right? A chemical reactor example, where we have here a chemical reactor where we feed products A and B, we charge it to the reactor, and the pressure gauge can measure the total pressure of the system. And what we want to estimate is the partial pressures of the 2 species. Now, you might say, okay, this is fairly simple, right? Just 2 states, but in fact, this has turned out to be a common benchmark example for nonlinear state estimation. Why? In recent years, because simpler estimators like the extended Kalman filter can actually fail in this example if you use very poor initial guesses for your states. So what we did actually was on a compact subspace of the state space, we verified this incremental IOSS condition, actually for a constant matrix P, right? Using these tools that I showed you before, using the differential dynamics. So actually, in fact, this example was used since many years by us and also by others, and this was always claimed that the system is in fact incrementally IOSS, but so far was never verified. So this we did in that paper last year for the first time. And now, interesting, if you then look, what are the resulting stability bounds for MHE? So I first have a result. This is actually an overview paper or in the handbook of MPC by Doug Allen and Jim Rawlings, where actually they consolidated at that time existing MHE schemes by them and by us and by others and improved them a little bit. And then the resulting horizon, which I need, is 142, which is quite long, right, I would say. Using a standard cost, right, a standard least squares cost without discounting and not with this Lyapunov type of analysis. Mainly because the analysis used by us and by others and Jim Rawlings' group at that time, right, over many years was, I would say, from the perspective now, quite nasty and complicated, directly using the definition with the K functions of incremental input-output state stability, but lacking really at the Lyapunov analysis. Now, when we first introduced the time discounting, right, a couple of years back, again, not using the Lyapunov analysis at that time, we could reduce a little bit, but not really significantly, right, the horizon. Now, there was a first very theoretically very nice paper, conceptually very nice paper by, again, Doug Allen and Jim Rawlings in 2021, where they actually did not really use a Lyapunov type analysis, but a Lyapunov-like analysis. It was time-varying Lyapunov function. It was quite complicated, but it was the first paper really introducing Lyapunov-like arguments into moving horizon estimation. And that's why I think conceptually this was very nice, but practically this was far away from being practically used, right? So more than basically 8 million, the horizon. And then using now this novel Lyapunov type analysis, the IOSS Lyapunov function basically as a Lyapunov function for the MHE, right? With these really designing the cost function according to the IOSS Lyapunov function actually resulted in a quite significant reduction in the required horizon, which I think 15 in simulation, it still shows good performance also, or stability, even for n equals 5. So there is still some conservatism, but I would say this is not really something that is practically relevant. And just to show you some of the estimation results, right? So this is the two states, right? The red one is the true system, and the blue one is an MHE with a slightly longer horizon, right, to have good performance. And the magenta one is actually the extended Kalman filter, which, as you can see, produces non-meaningful estimates, right? Because one of the concentration is estimated to be actually negative, which cannot, of course, not be the case. And the reason is that we have actually very poor initial guesses, right? So the one state which starts at 3 is initialized at, I think, 0.1 or something like that. And the other one which starts at 1 is initialized at 5 or something like that. And if you have these poor initial guesses, then it actually might happen that actually more so easier estimators like the extended Kalman filter actually fail. Now, this was a rather simple example, right? 2 states. So we also tested it on a slightly more complicated model, right? So this highly nonlinear quad-rotor model with 12 states, 4 inputs, the speed of the motors, the states are position, orientation, velocities, and we assume that we only can measure position, orientation, but not the velocities. And again, we could use here this tool that I showed you before, using differential dynamics to in fact verify incremental input-output state stability. And then we chose a horizon. I don't recall what was the minimal horizon. It was somewhere below 30. I don't recall the exact number, but n equal 30 in any case worked. And here, just to illustrate it right here, we estimated this helix-like figure basically. And just this here, a plot of the Lyapunov function, as of course guaranteed by the theory, it decays here exponentially to a region determined by the measurement mass, right? So this just to show you that it's also applicable, this Lyapunov framework, also applicable to more complex models used in practice. Of course, as is also without saying, right, really using that for really high dimensional systems is also not possible, at least as of now, right? Because as we all know, using these SOS techniques is also, of course, incurs the curse of dimensionality. But at least, so in this case, for a 12-dimensional system, it was possible, and we could achieve these estimation results. So before ending, I would briefly like to mention some extensions. Of course, the price to pay is you need to do online real-time optimization. Okay, right? If you can do that, fine. If not, then you cannot directly apply this, of course. And of course, this depends on the time scale, right, of your system, the sampling time. But we and other people have actually been working on real-time MHE schemes, right? So basically saying I don't do complete optimization, but only an incomplete optimization. I do 1, 2, 3, given any number of iterates I can do within the sampling time of my optimization problem, and still want to be able to ensure that I have stability of the resulting estimator. And there are some very nice works by the groups of Moritz Dier and also by Alessandri and Gagaro in recent years who actually exploit certain properties of specific optimization algorithms. I think Gauss-Newton algorithms, if I recall correctly, for example, in Dier's work. And so that they basically can show if I only do a fixed number of iterations, right, I still have local convergence. If I don't, so for the suboptimal estimation and not optimizing to optimality, of course. And we also took a look at that, using a little bit of different approach, right, in the case, which admittedly can be a strong assumption, but maybe in many applications, this can also be the case. If you have a very potentially poorly performing state estimator available, right, which gives a robustly stable estimate, we can then use basically moving horizon estimation to improve the performance, right? And we basically then show it basically by using some iterates of the optimization problem. Basically, we only can improve the performance, right, and cannot inherit the stability basically from the other estimator. And the other extensions that we have recently worked on is joint state and parameter estimation, right? While besides state estimation, we also want to estimate unknown parameters if we have parametric uncertainty. That also should be estimated online. And there has also been some old work, roughly 10 years ago, by the group of Tor Arne Johansson, where basically they did not use this Lyapunov analysis, which was not available back then, but basically designed an MHE scheme for just looking at the augmented state, right? Extending the state by a constant dynamics for the parameters, but the resulting conditions, right, which include, of course, some persistency of excitation condition, since otherwise parameter estimation is not possible, or not easily possible, right? But these are very difficult to check actually a priori. And we recently then exploited also that novel Lyapunov type framework, first in an IFAC paper last year, where actually we guarantee convergence under a uniform joint IOSS condition, which basically corresponds to a standard IOSS condition for the states and a uniform persistency of excitation condition for the parameters, as typically used in the context of adaptive observers. But of course, that might be restrictive, right? Because specifically in closed loop, you might not have such a uniform persistency of excitation condition. And recently, just a couple of weeks back, at the end of last year, we also submitted a paper where actually we relaxed that and allow for some online excitation monitoring, and then in particular an adaptive regularization, so adjusting these weights in the cost function, in particular the prior weighting, adaptively, depending on whether or not the past horizon was actually persistently exciting or not. So let me conclude my talk and sum up what I showed you, right? So in the first part of today, I discussed this notion of incremental input-output state stability and some time-discounted variance thereof, and mentioned or showed that it's actually a suitable detectability notion for nonlinear systems with direct relations to classical concepts of detectability, observability for linear nonlinear systems. It has an equivalent Lyapunov function characterization, which in the exponential case, we can verify using tools from contraction theory and then transform it into a set of LMIs, which we can solve numerically. And in the second part, I showed you that we can actually exploit this notion for the design of nonlinear state estimators, optimization-based state estimators, in particular that the cost function, which I use in the moving horizon estimation, should be or can be chosen directly in relation to the constants and matrices appearing in the Lyapunov characterization of incremental IOSS. And this then serves as an n-step Lyapunov function for the resulting estimator. Now, this allows us to actually prove that the estimation error is robustly exponentially stable, and also that it actually yields robustness guarantees under, I would say, practical conditions, right? In particular, not too long, unrealistic horizon lengths that were the case in previous results in literature. Now, with that, I'm at the end of my talk. I want to thank a couple of people. In particular, many thanks go to Julian Schiller. He's a senior PhD student in my group, and many of the results are presented today are from his work. Some of the results also were obtained with Sven Knüfer, who was a previous PhD student, now is at Bosch. And in particular, this Lyapunov framework we developed together with 3 people from the ETH in Zurich, Simon, Johannes, and Melanie, who, of course, I also want to acknowledge. And here are just some of the references that I managed. I display them briefly, so if someone later in the YouTube video wants to have a look at it, and these are the other references that I also mentioned throughout the talk. And with that, I want to thank all of you for the attention, and I'm happy to discuss any questions if there are any left. Thanks a lot.